Hey guys, so today we're going to talk thermal energy. And thermal energy is always really interesting, and it's just basically talking about the heat and everything that comes from it. So let's get through our notes. Make sure you're writing these down, and I believe that there is a note check after this lecture that you'll need to turn in. All right, so what is thermal energy? It's basically the sum, so adding together the kinetic and potential energy of particles in an object. So every single thing that's around us has particles in it. And the amount of thermal energy it has is however much potential and kinetic everything in an object has. So the bigger object, the more thermal energy. So my cup is going to have more thermal energy than the marker. And as things get hotter, they have more thermal energy. So if I stick my water in the microwave, I wouldn't, but if I did, it would have more thermal energy in it. And all that temperature is actually a measure of the average kinetic energy of particles in an object. So thermal energy is kinetic and potential, how much we are moving and how much we could move of everything that is happening in an object. But temperature is just the average amount of moving energy all the particles in an object have. So this marker doesn't have a ton of temperature, although there are still things moving around in it, so it does have some. Same thing with like a calculator. You pick it up right now, it's not the warmest in this room, so it is got a lower temperature because there's less particles moving in it. If I put water onto a stove and the molecules in it start moving and bubbling, then the temperature of that water is higher. So the higher the temperature, the faster things are moving. So when you're freezing something, you're essentially slowing down the movement in those molecules until they're moving so little that they can turn into a solid. When you're heating something up, like putting water on the stove, then the particles are going to move faster and faster, and that's what gets us boiling. So how do you know if someone's like been sitting in your chair? So like you go to your next class period and you sit down and it's like got that weird kind of gross warmness to it. You know that it's someone's been sitting there because it's warm. So thermal energy is always going to flow from higher temperature objects to lower temperature objects. So you as a person sitting in your bed or in a chair right now are around 96, 97 degrees. That's just our body temperature. And whatever object you're sitting on is probably not that warm. So the energy is moving from you into that object because it goes from hot to cold, always. So heat is represented with a capital Q, which doesn't make a lot of sense in English, but in other languages it does. And that's the transfer of energy from one object to another. So when we say something is hot or has heat to it, it's just the energy coming off of that object and going to something else. So like a fire has a lot of heat to it, and you know that it has heat because it's putting off that energy from it to you. And it's measured in joules because it's just another type of energy. So when we're transferring thermal energy, you need to know that there is really technically no such thing as cold. Cold is just, it's a word that we use to make things easier on us, but when you feel cold, all you're feeling is actually the absence of heat. So instead of saying like, I feel a really strong absence of heat, we just say, man, I'm cold. So we kind of changed it up, but really the idea of cold is just the absence of something else being there. So when you are holding a cold drink, like just say you made yourself a smoothie and your hand starts to feel that cold, it's actually because your hand is warmer than the drink. So the heat from your hand is putting the thermal energy into your drink instead of staying where it's at. So the heat is leaving it. It's like absent now in your hand and it's now into the drink. So when heat flows into an object, so when we go from something hot to something that's less hot, then the heat is going over where there is less of it, and it is making the other thing positive. So it's making the other thing warmer. Whereas when we're flowing out of an object, so when your hand is holding that cold smoothie, then the heat that is from your hand is flowing into the colder smoothie, and so that is a negative change in heat. We have 3 different ways that thermal energy can be transferred. The first one is conduction. So conduction is direct contact. So we're touching something and it's causing particles to get more or less energy based on what's going on. So solids are the best conductors of heat, and that's because your particles are closer together. So like when you put a pan on a hot stove, touching the stove is how we're transferring that energy. You can't just like hold the pot up and hope that it gets warm. It's going to conduct heat by touching the stovetop. And like I said, for solids, particles are already so close together that contact between the two is easy. So you can even have like a whole string, or let's think of like maybe a match. You light the match, and while you have the flame on one end, it's touching all these other particles and moving down. And so that's conduction, is those particles are touching each other to get that heat. And we have convection, and that's when we are transferring energy because hot particles are moving. So we have the convection cycle, which you guys might remember. And that's what's happening in this tea kettle, is we have the tea kettle being conducted onto the stove because it's touching the stove. But then the water molecules that are in it, when they heat up, they rise. And when they heat up, then they go to the top and the cold particles move down. So we're creating this cycle of the moving heated particles in that water, and that causes convection. It's actually the same way a convection oven works. So a convection oven is going to cycle the hot air into the oven and pull the cold air towards it so that we can create almost like a vortex of heat. This mostly occurs in liquids and gases because, like my water here, it's all kind of just sitting right here. If I heat up one part of it, then it'll convect all the way through the rest of it. It's going to create that pattern. And your currents move from warmer to cooler parts of the substance. So wherever it's warmer, remember we're always moving thermal energy from our warmer to our cooler areas. So we move around in a cycle until everything is evenly heated all the way through. Then we have radiation. And radiation is when we transfer energy through electromagnetic waves. And all electromagnetic waves are things that can travel through the air. So you don't have to be touching it, and you don't have to be convecting within it to be able to get the heat. So the sun and fire, when you feel heat off of that, that's radiation. When you are cooking something, baking something, and you pull it out of the oven and you put like your face over it, that's radiation because the heat is coming towards you, but you're not directly touching it, and you are also not like within it circling around. Radiation is going to happen fastest in gases, and it can be absorbed or reflected. So we can absorb the heat from the sun or a fire. When you wear black, you tend to absorb more of the sunlight, and that keeps you warmer. And it travels through space between our molecules. So the reason it travels fastest in gases is because gas particles are farther apart from each other. So there's more space for them to like just kind of shoot through, and they don't have to worry about bumping into like every single particle along the way like in a solid. So when we talk about it happening fastest in gases, the air around us is a gas. So that's how we can feel heat from a fire coming off of us, or not off of us, but towards us. So some materials are going to transfer heat really well, others do not. Our conductors are going to allow heat to flow easily. So we can conduct our thermal energy. The other way to kind of look at it is it's like a train conductor. Having a conductor makes the train flow better down the tracks. Yep, that works. So some examples of really good conductors when it comes to materials are metals. So obviously metal gets really hot when you put it over a fire or you touch it to something really hot. And then also your skin. Skin is a really great conductor, and that's actually how we can kind of keep ourselves so warm all the time. And then insulators don't let heat flow easily. That's the whole point, right? You want it to either have the heat stay trapped in there like in a thermos, or have the heat trapped outside like for a cooler. So air is a really great insulator. Now air is all around us, so we don't really notice that, but it is. When you look at like these Tervis cups, they sealed off like a pocket of air in between the layers, and that's what allows things to stay colder longer. Wood is a really great insulator. It's what we build houses out of, so we can keep ourselves warm in the winter and cool in the summer. Styrofoam, which is what a lot of coolers are made out of, plastics, and fiberglass. These are all things that are going to keep either heat in or heat out. So when we come down to specific heat is the amount of heat that it takes to raise the temperature of 1 kilogram of a material by 1 degree Celsius or Kelvin. They equal about the same. So if I have let's pretend this book weighs 1 kilogram, and currently it's sitting at 30 degrees Celsius. That'd actually be really hot. Anyway, if I wanted to raise the temperature of the book by 1 degree, how much energy it takes to do that is my specific heat. And it's going to be very different based on the type of material, because we have either insulators or conductors. Maybe we can heat things up really easily. Maybe something resists being warmed up. So we measure it by a calorimeter. And we're not going to use calorimeters. One, every time we try to do a lab, we tend to go remote. But also, we don't have them here. So what we're going to use instead is our equation, and that's Q equals MCAT. And that's not exactly what it means. The Q stands for our heat, or a change in our thermal energy. So how much heat or how much extra thermal energy we have to put in or take out of something, measured in joules. The mass measured in kilograms. C is our specific heat, and this is measured in joules per kilogram degree Celsius. And you only really need to know that because we need to make sure we're using joules and kilograms and degrees Celsius everywhere else. And then the triangle is just the change in temperature. So we can actually replace that and say Q equals MC, our final temperature minus our initial temperature. I would write both of those versions of the equation down in your notes so that you have it with the delta, which is our triangle, or instead have it say Q equals MC times parentheses your final temperature minus your initial temperature. And your temperature needs to be in degrees Celsius. So let's go through some examples real fast. We have a wooden block, and it has a mass of 20 kilograms and a specific heat of 1,700 joules per kilogram degree Celsius. Find the change in thermal energy of the block as it goes from 15 degrees Celsius to 25 degrees Celsius. So the first thing I'm going to do is write out all the variables and what they have given me. So I know my mass is 20 kilograms. My C, so my specific heat, is 1,700 joules per kilogram degree Celsius. My initial temperature, where I'm starting at, is 15 degrees Celsius, and then I end at 25 degrees Celsius. So I'm looking to solve for Q, which is my heat or my change in thermal energy. So how much heat do I have to put into this block to get it to go from that 15 to 25 degrees Celsius? So I'm going to use the equation Q equals MC delta T, or the Q equals MC times my final temperature minus my initial temperature. And this is how we're going to normally see it. So just plug in my numbers based on what we've been given and then solve it. And I'm going to get it takes 340,000 joules of heat to be able to warm that block up 10 degrees Celsius. All right, so for this practice time, number 1, The air in a living room has a mass of 60 kilograms and a specific heat of 1,020 joules per kilogram degree Celsius. What is the change in thermal energy of the air when it warms from 20 degrees Celsius to 25 degrees Celsius? So let me go ahead and get this put up on the board and we'll work it out. Okay, so I have my problem up on the side and then I'm going to do my work over here on the left. It might be a little hard to read if you're watching this on a phone, but hopefully you can kind of follow along. So I'm going to write out first the variables that they've given me. So I know my mass is 60 kilograms. My specific heat, which is C, is 1,020 joules per kilogram degree Celsius. What is the change in thermal energy? So that's my Q. I don't know what that is. When it warms from my initial temperature of 20 degrees Celsius to my final temperature of 25 degrees Celsius. So I'm going to write out the equation I'm going to use. Q equals MCAT. But I'm going to go ahead and replace the delta T with my variables. So Q equals M times C times my final minus my initial temperature. And then I'm going to plug in my numbers. So I have 60 times 1020 times 25 minus 20. Make sure that you are still following your order of operations. So we want to solve this part first before we multiply everything else. You can try typing it in your calculator the way it is. I don't trust my calculator to think on its own and make sure it follows all those order of operations. So I would do my 5 over here and then multiply them all together. So 60 times 1020 times 5. So my thermal energy, change in thermal energy, is 306,000 joules. And that is going to be my answer for practice time number 1. Now let's move on to the next problem. The thermal energy of water in a mug increases. So my change in thermal energy is increasing by 12,552 joules when the water is heated from 20 to 40 degrees Celsius. So I started at an initial temperature of 20 degrees Celsius and I ended at a final temperature of 40 degrees Celsius. If the specific heat of water, so that's my C, is 4,184 joules per kilogram degrees Celsius, what is the mass? Okay, so I'm going to write out the equation. Q equals MC delta T. I'm going to put in my final minus initial temperature. And then I'm going to go ahead and plug my numbers in. So 12,552 equals M, because I don't know what that is, times 4,184 times 40 minus 20. So if I go ahead and condense this side down, I know that this number right here is 20, so I'm going to multiply those two numbers on that side together. So 4,184 times 20. So I have 12,552 equals M times 83680. Now I need to solve for M and get it by itself. Right now it's multiplied with something, so I'm going to divide by that number. So the mass of my water is 0.15. And if I forget what units I'm supposed to use, I can always look back over and see what I wrote down. So I see kilograms here. And because I've already used that in my equation, I know that this is going to be kilograms here. So I have 0.15 kilograms of water to fit that format in that equation. All right, so that's the last practice problem. Make sure you have these notes written down and you submit a photo so you can get some credit for it.